Hello. So carrying on with the lecture that we began last time, and last time we were looking at comparing three different winding fractional slot windings. So we had a 6-slot non-overlapping winding, all teeth were wound. We had a 6-slot non-overlapping winding, alternative teeth wound, and then we had a 12-slot distributed winding. These two had half a slot per pole per face. This one had 1 slot per pole per face because we were trying to design the winding for creating 4 poles. So starting with So in this lecture, in this section, what I'm going to do is I'm going to derive the Fourier series for all 3, and then we will look at the harmonics, and you'll see how these fractional slot windings can work. So if we look at the winding function from last time for B, 6-slot non-overlapping winding, alternative teeth wound, we obtained this winding function. So that doesn't look like it's creating 4 poles, 2-pole pairs, right? This is looking pretty bad. The magnitude here is higher than on the negative, but the areas are equal. So in order to understand the harmonics for this winding function, we should use a Fourier analysis. So we could change the starting position for the winding function so that it starts at 0. Where it goes up to the peak and then comes down. So rather than changing it minus W over 2, we move it across by W over 2. And so this here will be W, and then the rest of this is negative part is the same until 2 pi. And so this would then repeat. This negative here is located at minus n W over 2 pi, and the positive here is in W1 minus W over 2 pi. Now, there's a little bit of confusion here, I'm sorry, but the number of turns, I've been using the notation n subscript W, and I used that, I'd subscript W so that to differentiate from the winding function, which is n. But here we also have the pitch, slot pitch W, so that comes into these equations. So this here is n subscript W times by W, the slot pitch. Okay, so in order to analyze this, we want to look at the harmonics. So we could use the regular Fourier series. What I'm going to do here is use the complex Fourier series. It allows me to calculate both the sine and cosine harmonics together. It's actually easier. So Fourier series for the non-overlapping. This is B I'm doing B first, and then actually we'll be able to get A quite easily. So Fourier series for the non-overlapping winding with alternative teeth wound. So the exponential form of the Fourier series, the exponential form of the Fourier series is given by, for the Whining function, is evaluated for the, so we put real here, and then that's the summation from minus infinity to infinity of this here. Hi, sorry, I'm recording a lecture. Would you just mind just keeping the noise down, please? Appreciate it. Thank you very much. So the exponential form of the Fourier series is shown here, and then the Fourier coefficient, complex Fourier coefficient, is defined as 1 over the period, and then we integrate it across a period where f theta is the function that we that we are evaluating. So in this case, it's going to be the Whining function here, right? So the k naught is equal to 2 pi over the period, and in this overlapping, non-overlapping alternative teeth wound, we can see the period goes to 2 pi. So to t is 2 pi, and so therefore k naught is going to be 1. Okay, so now let's evaluate this where this where this f here is the Whining function shown here. So we're going to try to obtain the Fourier series for that. I'm not going to try, we are going to do it. Okay, so then the and t naught, so t naught can be taken as 0 in here. T naught equals 0. So then so we have two parts to evaluate. And so the Cn is going to be equal to 1 over 2 pi, the period, and then the integral we're going to evaluate from 0 to w, and then that's the magnitude is n subscript w 1 minus w over 2 pi, and that's e to the minus j n theta d theta. And then the second term is evaluated from w to 2 pi, and that's n sub w times w over 2 pi e to the minus j n theta d theta, like that. Okay, So now evaluating the integrals, we get 1 over 2 pi. I'll take out the NW. So then we have NW times 1 minus W over 2 pi e to the minus j in theta divided by minus j in, and that's evaluated from 0 to W. Okay, then we have a second term minus NW over 2 pi times W. I'm sorry about that notation, it is confusing. I haven't taught this class very much, but that's, I guess I should, maybe N should be N sub A for A phase. That might be clearer, right? So then we have e to the minus j in theta divided by minus j in, and that's evaluated from 2 pi to W, like that. Okay, now I'll carry on with this. So then substituting in the limits, and then I'll put the j on the top so I can multiply j by numerator and denominator, and then so j times j is minus 1, so that gives us j. So we have j in subscript w divided by n times 1 minus w over 2 pi, and then that's times e to the minus j in w minus 1. That's that first term, and then we have minus j in w big W divided by 2 pi times e to the minus j in 2 pi minus e to the minus j in W. Like this. Okay. Now we can note that. So note that e minus j in 2 pi is equal to cosine in 2 pi minus j sine in 2 pi. So this is always going to be 0. This is going to give us a 1. Okay? So this will give us a 1. Now if we look then here, actually let me expand this one out one more step. So this is 1. So let me expand that out. So I'm continuing. I'm going to expand out these two terms. So we get 1 over 2 pi j in W in sub W e to the minus j in W divided by n. That's the first term. and then we've got the 1 times 1. That gives us minus j n sub w divided by n, and then we've got the exponential term minus j n w w divided by 2 pi n e to the minus j n w, and then we've got the fourth term, which is j n w big W divided by 2 pi n, and then we've got the last two times minus j n w big W divided by 2 pi n, and that's multiplied by e to the minus j n 2 pi plus j n w w over 2 pi n e to the minus j n w. Okay. Alright, so we said this was 1. There's 1. So looking at these two, they're going to go away, right? And then this is j n w w over 2 pi n to the minus. It's the same, but there's a minus in the front. So these two go away as well. And so it simplifies down nicely. So then we get finally that Cn is equal to just these first two parts, so that nw can come out and the j can come out. So we have j n sub w divided by 2 pi, put the n there too, and that's multiplied by e to the minus j n w minus 1, like that. So therefore, so we can now substitute back in the complex Fourier coefficient into the complex Fourier series, and we get out n theta is equal to the real part of summation of n equals to minus infinity to infinity j n w over 2n pi e to the minus j n w minus 1 e j n k naught theta, like that. Now it would be nice to write this in terms of real terms only and then find the magnitude part. So let's keep going. If we multiply these, we can replace these exponentials with sine and cosine terms. So keep going down the rabbit hole. We have j n w divided by 2n pi, and I'm just going to write this out in a longer way. E to the j n w, e to the j n k naught theta minus w minus e to the j n k naught theta, like that. Okay. Now let's expand this out into cosine and sine terms. So we have n theta is equal to the real part of equals minus infinity to infinity j n w to n pi times cosine n k naught theta minus w plus j sine n k naught theta minus w minus cosine n k naught theta minus j sine n k naught theta, like that. Okay. We can now we're only interested in the real parts, so we can then simplify this down further. So doing that, we have NW. Let me leave that in there. We're going to take the real parts only. So this is j times cosine, so this is complex. J times j, that becomes real, so that one exists. So let's write that in. So we have, well actually, let's just keep going. So the j times, so this one doesn't exist. J times this one, that's going to be complex as well. J times this one is going to be plus. This one's going to be a plus sign. So let me write plus this one first because of the plus. So it's plus, so it's sine n k naught theta, and then this one is minus sine n k naught theta minus w. Like that. Okay? Now rather than summating from minus infinity to infinity, you know, there's going to be harmonics on both sides, right? But they're going to be symmetric for the complex Fourier series, if you remember. So we only need to the first half, but if we do that, then we need to multiply this magnitude by 2 because to accommodate the both magnitudes. So then if we do that, then the 2 goes away there. Fair enough? Okay. Now this is sine minus sine, so we can use a triggered entity to combine those. So let's do that. So we have n sub w pi, and then n equals 1 to infinity. So we have 1 over n, and then so the sign and these two signs, they you add the terms and you subtract the terms within the signs, and then we get, using the triggered entity, 2 times cosine 2n k naught theta minus nw divided by 2 sine nw over 2, like that. Okay, so let's, like, finally, well, let me just rearrange that. So this sine term here is part of the magnitude. So we have sine nw over 2 divided by n. Oh, and sorry, there's a 2 here, so that comes out. So we have a 2 here, 2 in W over pi. That's that 2 here. That 2 comes from the triggered entity. And then, so that's the magnitude term, and then that's multiplied by the spatial term, because it's a function of theta. You may be wondering why I kept k naught in. Remember, k naught in this case is 1, because k naught is 2 pi over the period, and the period was 2 pi. But for the next case, we can actually reuse this equation for the second part, so that will be helpful. So before going over this, I'm going to go over the other 2 windings. So Fourier series for non-overlapping winding with all teeth wound. So in this case, we had the winding function looking like this. So this was NW 1 minus W over pi, and the negative value here was minus NW W over pi, and this is located at W over 2, and this is pi minus W over 2. So that's what we had. Now again, makes more sense to shift the winding function so that it starts it starts at the same place. The transition begins at 0 angle. It just makes life a lot easier. So then this is W, and then this is pi, and then this is W 1 minus W over pi. So the main effect of this is actually is actually to change the period here. So this period is to pi rather than 2 pi. This magnitude here has got a pi rather than 2 pi as well, right? So instead of t being 2 pi, t is pi, and so therefore k naught becomes 2. Okay, so we can use that. So we can use the same winding function pattern, Fourier series that we used before, which is helpful. So then, okay, and I'll show this in Mathcad in a minute. Just want to show that in a minute all together. So then the last winding we're going to analyze was the Fourier series with the 12 slot overlapping distributed winding. So let's now do that. Fourier series for 12 slot overlapping distributed winding. Okay, so we have here the winding function, I'm just going to go straight to it. Again, we did this. So we have this winding function where this would be pi over 2 pi 3 pi over 2 pi. And you can clearly see that this more clearly can create a sine wave. So then the winding function for this is just going to be 4n pi times the summation n equals 1 to infinity sine n 2 theta. The 2 comes about because it's two pole pairs, and n is odd. So now I'm going to show the Mathcad simulation. Okay, so we had three windings we were looking at, and so what I did is I wrote up the let me make this a bit bigger. You just have to look at this, the slide on the left side. So this is the here, this NA. This is the equation that we derived for the non-overlapping winding with alternative teeth wound. On the right side here, I did it also using cosine and sine terms, and they match. So this is the winding function where n is from 1 to 500, and you can see that it creates quite a nice accurate winding function plot. Then I found, and so then from this you can see what the magnitude is. It's going to be 1 over n sine times n w over 2, and then from that you can write out the magnitude term and then look at the harmonics that are present, and there is a lot of them. Look at them all. There's an awful lot of harmonics. Now then, if you, so down here I plotted the field, the winding function, and then I also plotted the first three harmonics associated with the winding function, and you can see this is the first harmonic here, and then in green is the second harmonic, and you can see that this one indeed creates a north and a south, pole. So the second harmonic will therefore be the one that interacts with, if you had magnets on there, that would then interact with the magnetic rotor to create torque. So it's not the fundamental that interacts, because that's one pole pair. It's the second harmonic created by the winding function. Okay, and then below here I have the winding function for the non-overlapping winding with all the teeth wound. So it's the same thing, same type of form, except that it repeats. So the period is pi rather than 2 pi, and so then you get a similar type of waveform, but the fundamental is the one that is creating the 4 pole pairs, not the second harmonic. And then if we compare that with the 12 slot here, you can, a 12 slot overlapping distributed winding, then the difference is quite clear. The fundamental is shown. So in this one, only the odd harmonics are present, and so the fundamental is the main one, and then you get the third, fifth, seventh, and so on kicking in. But you can see there's quite a difference in the number of harmonics. The concentrated winding has a very rich source of harmonics. That is going to create a lot of eddy current and hysteresis losses if you're not careful with the design. So if you're designing for a concentrated winding machine, you have to be very careful with regard to minimizing the losses in the magnets. For example, you need to probably almost certainly segment the magnets. So rather than one big magnet, you would have multiple magnets, and that would then reduce the losses significantly. Okay, I'll stop there.